Good afternoon. My name is Angela Boudewijns and I will like to welcome everybody to this webinar. For today's webinar, we are pleased to have Professor Nagel from University Clinic Frankfurt, Main in Germany, who will give a presentation, also a live demonstration. Professor Nagel will share his view on the role of strain for clinical routine measurements, and also he will provide a demonstration of a simple and quick workflow to measure strain. So we would like very much to forward to his presentation. In addition, we have David Houteman as panelist in the webinar. David is product manager for the MetaSuite MR product and is also there together with Professor Nagel to answer any questions you may have. So when you have any questions during the webinar, feel free to use the Q&A section. We try to answer those questions throughout the webinar or after the demonstration. If there are unanswered questions, we will make sure to email them afterwards. This webinar will be recorded. We will send a link to every registrant afterwards. Now I would like to give the word to Professor Nagel.
Hello, everybody. Good morning or afternoon or evening, whatever your time zone is. You're very welcome to this webinar about strain quantification. I will start with a couple of slides to lead you through the background of strain and how it's quantified with MR, and then we have several live cases to go through the quantification process, which is actually quite straightforward, and we will also do a little bit of reproducibility analysis. I would start with the slides, go through the background of what we do. In principle, with MR, or in general, when we do tissue tracking, what we try to do is discriminate the various motion components of the myocardium. There is a strain, which is supposed to be more based on the endocardial fibers. There's circumferential strain, which is supposed to be more due to the contraction of the epicardial fibers. The two directions in total then create the heart to contract and create the ejection fraction. We're mainly going to focus on longitudinal strain today. What has been shown is then longitudinal and circumferential strain are probably the two most robust versions we have at the moment, more robust than, for example, myocardial thickening or rotation and twist. Now, the original idea here is that when you have problems with your endocardium, your subendocardium, for example, ischemia, then longitudinal shortening will go down, whereas circumferential shortening will go up to compensate for the reduction of global longitudinal shortening, which will then result in a normal ejection fraction. Or in another way around, if you have a patient with normal ejection fraction, it may actually have reduced longitudinal shortening with a compensated increased circumferential shortening. And that's the main part we're looking for. I do not believe that this only occurs in ischemia, and I don't think it's so much related to the endo versus epicardial arrangement of fibers, because they also cross each other. But it is important to understand that longitudinal shortening seems to be more sensitive than ejection fraction to show that something is wrong with the heart. In contrast to echo, MR doesn't have any speckles. So we can't do speckle tracking because the signal we get from the myocardium is actually quite homogeneous. So what we actually do in MR is we use feature tracking, and that is in principle focusing on endocardial features of the myocardium, such as the mitral valve plane, the apex, the insertion points of the papillary muscles, and other endocardial features. The algorithm then in principle takes a box and looks if a point is detected at one part of the cardiac cycle in another part of the cardiac cycle, and as long as that feature remains in that box, it will track it and then create a new box and a new following pathway for that particle or that feature over time. Now, it is important, this difference to echo is important because there are a couple of issues with MR feature tracking which make it different to echo speckle tracking. The first is that speckle tracking actually overcomes a problem of echocardiography, which is that you do not see all segments perfectly well to calculate ejection fraction. And if you then use a measure which in principle represents ejection fraction, you will have more accurate measures than just guessing the parts you don't see. So for echo, you overcome a limitation. For MR, you do not overcome that limitation because we don't have that problem of not seeing all the segments very well. The second is because we don't have intramyocardial features, as just explained, we do an endocardial tracing only, which has influence on, for example, if you have a patient with significant wall thickening, then the endocardium responds stronger than the mid-myocardium or epicardium, which is something we need to take into account when we compare our data to echocardiography. The recently published paper on endpoints in clinical research has in principle said that the evidence for the use of CMR-based strain imaging techniques is promising. They, and I'm one of the authors, weren't enthused that much because the number of validation studies is still relatively limited. And in addition, the normal values are relatively spread out. Here are shown some studies which have looked at reproducibility in healthy volunteers, and you can see that the inter-study observer variability here was 26% was actually not the greatest. Also, if you then look here at normal values, you take the mean minus 2 standard deviations, you come up with quite a large range of normal values. And that has, for quite a while, reduced my enthusiasm on strain. However, there are quite important data coming out demonstrating that the use of feature tracking improves our decision-making and especially improves our prediction of outcome in comparison to late enhancement and ejection fraction. So in this very large study here, in looking at patients after myocardial infarction, longitudinal strain was associated with MACE. It was superior to ejection fraction at LGE. In this study, which came out last year in JACC Imaging, which is so far the largest multi-center study, a couple of other features were shown. First, the reproducibility in multi-center setting can actually be done in a reasonable range with about 17% inter-observer variability and about 15% intra-observer variability. And more important, in this large study in patients with reduced ejection fraction, ischemic and non-ischemic cardiomyopathies, global longitudinal strain, when significantly reduced, was a strong predictor of outcome. You can see here that it adds to the information from ejection fraction. So you have ejection fraction of more than 35% and a preserved longitudinal strain, the outcome was good. If you had a reasonable ejection fraction and your strain was significantly reduced, the outcome was much worse. And if you have reduced ejection fraction with normal longitudinal strain, you were also still doing quite well. Whereas you have reduced ejection fraction and reduced global longitudinal strain, then your outcome was significantly reduced. Given that, and the fact that we are now able to do the quantification very quickly, I do see a strong role of feature tracking in clinical routine to confirm abnormalities and also to work on those patients where you don't know if there's maybe some diffuse myocardial disease. This is especially valuable, I think, for those of you who don't have mapping available or who do not trust the mapping technologies yet, because you can do it without the maps, you can do it on retrospective data, and you can do it very quickly. So what I would want to show you now is going through a quantification process. Okay, so I'm going to load a data set in the MEDIS software. I have pre-sorted them so we only have the long axis views here. The viewer comes up first, so you can get a quick idea of the quality of the scans. You then load them into QMass to to draw the first set of contours. You have to make sure you're in long axis function, and then in principle use a 3-point click, marking the mitral valve at the base, marking the apex, and you get an automated contour of the endocardial border. You then find your end systole, just the one before the valve opens. Again, you click on the mitral valve position and get the automatic tracking. Here you have the papillary muscle making a bit of difficulty, so you will have to bring that contour a little bit inwards. Then you go to the next view. Again, you do the basal slice, mark the mitral valve, mark the apex. You find your end diastole, end systole, mitral valve. If there is no clear insertion point of the mitral valve, I use the part where the thick part of the myocardium ends, so the beginning of the membranous septum and the apex. And then here again, it struggles a little bit with the papillary muscle, so you would pull that out. Then two-chamber view, mitral valve, apex, and systole, mitral valve, apex, and I would also bring that out a touch here. Once you have done the contours and you're at end diastole and systole and you're reasonably happy with them, you go into the feature tracking module, which does an automated analysis. You load the views into the long axis viewer, and then it will process the contours. It is important to mark the mitral valve properly because the length of the total length of the endocardial contour is quite important for the final results. You then have to, at the moment, accept that this is not an approved tool. Then you need to find end systole. I use the part where the ventricle is smallest, so I will shift this here to the part where the ventricle is smallest, and then you have your tracking here. You get a 3D display of what you see here, which sometimes is nice, especially to see if there's certain areas which behave very different than the rest.
Yeah, unfortunately, in this webinar, for some reason, the 3D model is now not being shown. But left lower corner, there should be a 3D model normally available.
Okay.
Yeah.
But it does show the rest.
Yeah, it shows definitely the rest. Yeah.
Okay. So here we then have a quick look at the contour. It's not important that the contour is perfect for all myocardial phases or for all cardiac phases. It is important, however, to check if the mitral valve position is relatively reasonably tracked, and if there are sort of significant shortcuts that somewhere the ventricle is, the apex hasn't been found, or there is significant overlay over the myocardium. If that's the case, you need to go back to your original contours and potentially modify them. So I would think the two-chamber view here looks good. The three-chamber view here looks reasonable enough. I would check if you can see here that this insertion point of the mitral valve jumps a little bit, but I would think that's after systole, so it should not have an influence on the end systolic value. And here's the four-chamber view, again, reasonably tracked. So we can then, in principle, look at the global strain and the ejection fraction. So here, ejection fraction is 60.8, and the global longitudinal strain is 24.8. Can you see this graph here? I hope you can see this graph.
Yeah, so we can see.
Because I like this graph a lot. It shows the expected longitudinal shortening versus your ejection fraction. Because if ejection fraction is high, you would also expect a higher longitudinal shortening. And if ejection fraction goes down, you also at some stage expect a lower longitudinal shortening. So if your data point is relatively close to this green line, it shows that the ejection fraction and the longitudinal shortening are concordant. Whereas when the longitudinal shortening goes down and the ejection fraction is still preserved, you will find a larger distance of this data point to this green line, which I find very very important and very interesting to look at. What I would suggest to do now is quickly go back and do the same case again, just to look at how well do we do with reproducibility. So I'm just going to delete all the contours, and then I'm going to start doing the contours just once more quickly to see how well are we doing if we do the whole thing twice. And it also shows that when you focus on making those points, you can actually do this relatively quickly. So obviously when there are no contours available, then it has a bit of difficulty finding them, but if you look here at the cine, you will find that actually the contour I drew is relatively close to where you would really think the endocardium should be. Okay, and then we go back into the module. We load the cases again.
I will just comment here because it's a blank purple screen here, but what you should see is a way to select the cities that were traced and drop them in the right long axis viewport. So it will be clearly indicated that you can drop the 2-chamber cine in the 2-chamber viewport and so forth. And after that, you will load everything here in the strain application. Also, in the meantime, if anybody has any question, please feel free to ask.
So now we have the second analysis ready. Ejection fraction is now 60.9. I can quickly show you the first one here. It was 60.8. Here we are back to the second one, 60.9. Global longitudinal strain minus 25.06, and the first analysis minus 24.8. So very similar results done as you were seeing live with two new contours. Or
we have one question, Professor Nagel. Does the usage of epicardial contours cause any problem?
I cannot answer that properly because we don't do myocardial thickening or radial strain. Radial strain has been shown to be not very reproducible because it relies on relatively thin structures, and any small mistake of one voxel will already cause about a 10% error. And you can see here that you can easily get a few voxels off with the current tracking mechanisms. So if you really want to do radial strain, you have to place your contours with much more effort. Whereas the longitudinal strain, which is based in principle on the length of that contour, is highly robust and highly fast. And it seems to be the one which has most clinical information. Okay, so this one I think quite nicely demonstrated that at least in good image quality data sets, we can achieve a high inter-observer or intra-observer variability. Let me then show you a different case. I'll go into this one first. So with this one, you can see ejection fraction is down quite a bit. I'm going to, again, load the contours and do the analysis. So relatively fast analysis. Again, check for the end systole. It's a bit of a hypertrabeculation here. And here, okay, this one needs some correction here. And so when the image quality is worse, for example, post-contrast injection, the tracking will be less precise. We tend to do the images we use for feature tracking before we inject contrast agent, whereas we used to do most of the cine imaging post contrast agent. So we have changed that when we do want to do feature tracking. So here again is the screen, which then allows me to load the images quickly and then go into the post-processing tool. And I accept, and then here I am at end systole. I'll show you the contour again here in the 2-chamber view, in the 3-chamber view, and in the 4-chamber view, and I think they are reasonable. Now, what I found interesting in this patient is that actually the ejection fraction was better than I thought it would be visually, with about 50% here, but the longitudinal strain was worse than expected. You can see here that the distance of the longitudinal strain versus the ejection fraction is relatively, or versus the expected longitudinal strain is relatively high, demonstrating that there is a predominant longitudinal problem in this patient. And actually, this is a patient from a study we're currently doing, looking at patients with HFpEF or diastolic philic abnormalities. And this patient then had a pressure volume loop examination, which also showed significantly raised end diastolic volume pressure relationship. So the reduction of the longitudinal strain related very nicely to this invasive finding. What I usually don't do, but I can quickly show you, is look at regional function. You get all the regional information for the different segments shown as well, and you can look at them individually. You can take some out. You can get other quantification tools here. The reason I'm not going to go...
Unfortunately,
yes?
we cannot see the screen, probably due to the Zoom.
Okay.
It's not showing that.
Okay.
Yeah, normally it will be there. Yeah.
Then I'll just go back and explain quickly. So you can get regional information with all these lines here for each of those of the myocardial segments. We don't do that because it is less stable at the moment. The variability is still a touch too high to be used for clinical decision making. And when you then have one segment which doesn't work properly, you then never know if this is just due to the tracking because there aren't that many features, or if there's a real regional wall motion abnormality, which you don't, which you would usually, if it's real, see already in the cine images. But this part here, to get the global longitudinal strain versus ejection fraction, is a very helpful tool to see if there's something wrong in the myocardium which you maybe didn't expect by just looking at ejection fraction. I have more cases, but we are also moving towards kind of the end of the time. So I think maybe it's better to take questions and if needed, look into 1 or 2 more cases to demonstrate the question.
So there is a question. So is it possible to derive any atrial strain measurements from this software?
Atrial strain? Yes, you can get atrial strain. It's in principle the same. It's the same principle. Unfortunately, I can't show you this loading screen because it only shows up as a blank screen for you. But you can do the contours in the atria and then load it into an atrial contraction tool. The principle, again, is the same. It in principle measures the length of that endocardial contour, and by that calculates a strain, and you can then differentiate the different parts of the atrial filling and contraction phase.
Yeah, I'd like to comment also that the tracking works in a very similar manner to the ventricle, and actually it's even easier because you don't have the trabeculations in the atrium, so it's even easier to get the contours in the right place.
Okay, the next question. How does CMR data compare to echo-derived strain?
There is very little data so far looking at that. And there are, with both techniques, MR and echo, there are considerable differences depending on the vendor you use to do the quantification. And as there have been ongoing efforts in echo to standardize things, these efforts are also happening on the MR side. But you always have to remember that we, with MR, measure subendocardial strain only, whereas with echo, you measure either an average strain throughout the myocardium or you measure the different layers. And that's an important difference which just has to be taken into account.
So maybe in the meantime, there are some more questions. Maybe I can take one, for instance, what is GRS and what is SDLS peak? GRS stands for global radial strain, and you would actually need a epicardial contour for that as well to measure the radial strain. However, if you noticed what Professor Nagel was showing, there's an asterisk in front of the GRS. It's an estimate of the GRS based on the endocardial contour motion only. So that is GRS. And the SDLS peak, that is an index. It's a standard deviations of the longitudinal strain, or actually the peak longitudinal strain of each segment in the 70 segment model. So this is an index that can give you some information about the synchronicity of the heart. One of the questions is also why is GCS or endocardial global circumferential strain reported from the longitudinal views? That's an interesting question because you would need it from the short axis views, that you're probably familiar with that. But if you have 3 long axis views and 3 contours, that means they would have 6 points crossing the short axis. And from those 6 points, you can also derive a circumferential deformation or a circumferential strain. So it is not the classic way of doing it, but the nice thing is you could actually get that information quite nicely on GCS for free with your global longitudinal strain. But that's how it is possible to measure that. Professor Nagel, would you be able to demonstrate still maybe the atrial strain analysis? No, we didn't prepare this, but maybe it's possible to show this live using the same Q mass and placing the BBA marker in the atrium and not in the ventricle. You could try that to show that. So let's see. It's a bit challenging without the sound, but let's see. That will answer a couple of questions actually coming in. So while Professor Nagel is doing that, which is the reference paper for the graph comparing global longitudinal strain and ejection fraction? There is a more technical paper on that, which you can send out the reference to that later, that looks at constant shape contraction, explaining this concept. So at this point, Professor Nagel is tracing the atrium, and also in 2 phases. I will just comment, and probably need to give the contours a little nudge here to get them in the right place. And then once that's done, actually it can be done in all 3 chambers. You could also do it in 1, and then the contours and the data can be loaded into the QStrain application. So when going now to QStrain, what you cannot see unfortunately at the moment is that you can pick which analysis you want to do. So there's a dedicated 2-chamber long axis view for the atrial strain, but you could also kind of misuse the left ventricular strain analysis and load 3 atrial strain contours in. And so it's going to be a surprise what Professor Nagel is picking, because we cannot see. But what we see is he loaded in one the 4-chamber in this case, and showing here the strain curve in the 4-chamber view. And think what's important is when you're going to quantify here strain, it's very important to put the ED and the S markers in the place where you actually want to measure your strain. So if you want to measure the, how do you call it? You have the conduit, the reservoir, and the booster pump. So if you want to measure the reservoir, the complete strain, this is what I believe Professor Nagel now is showing. You have the strain value of 11 or 12%. And if you want to measure the conduit or the booster, you just place the markers where you believe the phases are located. And that way you have a flexible way to investigate all the different strain values. Our package has a dedicated left atrial strain based on the 2-chamber, but you can be flexible and load in the 4-chamber or 3-chamber. Everything, in that case, it's very practical, and that's still because it's a research package.
So there were several questions that came in during the webinar. Unfortunately, we had some technical difficulties. So we are, after the webinar, recording now some Q&A with Professor Nagel. And one of the questions was, and now do you think eventually that a strain analysis would replace a classical cine analysis? I assume something like an ejection fraction?
We don't know yet, but if I look at what's important during an MR scan, I believe that it's more important to invest time on perfusion imaging and late enhancement imaging than actually on left ventricular function. For research studies and for follow-up studies, an accurate function is really important. But for most clinical patients, the function is in principle only classified in normal, mildly reduced, severely reduced, and it's also done in principle sufficiently by echo. So I think if we have an MR ejection fraction which reaches the same quality or maybe is a touch superior to echo, and we can save a significant amount of time during scanning, this could potentially be done based on 3 long-axis views and then just do the strain analysis. But this would need to be tested.
Now, there was another interesting question. What would be needed before feature tracking CMR could be implemented clinically?
I think we're there to use it clinically. We need more studies to compare it to ejection fraction and see if the feature tracking values are similar or superior. But the first larger scientific studies show that feature tracking actually is a better parameter to predict outcome. So I think we can start using it. In general, the issue there is that most of the cutoff values used clinically to determine, for example, whether a patient needs ICD or not, is based on echo ejection fraction, and MR really needs to fight its way in there. And the more we have tools which are robust and easy to reproduce and fast, the higher our likelihood is to actually find ourselves a place in clinical routine for those questions. So I think it's something where we should just push to move forward and potentially start tackling echocardiography as the core technique for the first-line analysis of these kind of patients.
So the next question is, what is the reference paper for the graph comparing the global longitudinal strain with ejection fraction? Well, this paper is from the Journal of Biomechanics, was published in 2014 by Professor Gianni Pedrizetti in collaboration with Gian Mangual and Giovanni Tonti. And this paper, you can see here the title in the screen. And we will also mention the link in the description in the YouTube video. So that's how you can look up this interesting graph, the background. Next question was whether the standard deviations longitudinal strain peak values are reproducible and whether they're useful, and how is the asterisk for the global radial strain generated? Well, the already this was answered a bit in the previous question. It's something for an index that could be used at the moment for research. At this moment, I don't know whether there's data on the reproducibility, but it's something that could be taken into account when studying synchronicity or asynchrony of the heart. And asterisk GRS, so this is the global radial strain estimate based on the endocardial contour tracking only. So you would need actually for global radial strain the endo and epicardial contours. If you do not have the epicardial contour, as Professor Nagel already explained earlier, for longitudinal circumferential strain, you don't really need that. It's better to base it in MR on the endo contour. So we can estimate this GRS from the endo contour motion only. Now the final question that we had was about right atrial strain. There were in the 4-chamber, if you would only draw it in a 4-chamber, to what extent could that affect the accuracy of the measurement?
So you can use several long axis views to determine right atrial strain, and that is more robust than using just a 4-chamber plane. The main reason is that in principle 3D is always more robust than just using 2D. And the second risk of using 2D 4-chamber plane only is that especially the 4-chamber view is highly dependent on the breathing position of the patient. So if they have a different breathing position, then the imaging plane may be out of the accurate 4-chamber view. This is a risk for the longitudinal strain of the ventricle, but it's also a risk for the right atrial and left atrial strain. So you should be careful doing that. But if you have a well-placed 4-chamber view, which you can assess visually, then it is the best view of the possible views to analyze this strain.
Okay, thank you very much for answering all the questions, Professor Nagel. And I think we can conclude the webinar.
Thank you very much for attending, and I hope it was interesting and you did get answers to most of your questions.